Okay, so first let me get some introduce some background knowledge. First is the protein ligand modeling, and as you know that predicting the strength of a candidate drug, a drug molecule's interaction with a target protein is a challenge but crucial task for drug discovery applications. In order to represent them, there are several choices. For example, the row-dimensional representation, such as linear sequences, is 1D, or chemical bond graphs is 2-dimensional, or some more advanced representations, such as considering the 3D positions of the component atoms, allows for better modeling of 3D shape. Today's topic focus on the deep learning side. So we mainly take review of the deep learning models, and they can be roughly divided into 3 categories. First is the sequence-based modeling, including the deep DTA, the proto-chance. For deep DTA, you just feed the smiles of small molecules and the residual sequences of proteins into convolutional neural networks. Then you concatenate the representations and forward them into a multi-layer perceptions to predict some properties, right? And the proto-transformer just is based on the popular transformer architecture. So they use the self-attention mechanisms to capture the interactions. For sequence-based models, their strength is obvious because the protein sequences are very abundant. There are more than billions of protein sequences, so you can extract meaningful semantics via self-supervised learning, right? But for weaknesses, they fear to make full use of the explicit geometric information, right? So a more advanced choice is to use the structure-based modeling, such as the graph vector perception, GN, or 3D convolutional neural network. Their strength is also maybe lies in that they are capable to capture geometric interactions, but their weakness is the structure data is limited. Their data sets cannot be very large, right? So another interesting line of research is the hybrid modeling. They use such as the holoprotein. They use both the surface and the structure to build graphs and predict some interesting fitnesses of proteins or binding affinities. Use this hybrid representations. So now let's go to the motivations of our work. The latest biological discovery find that the initial lock and key theory of ligand binding is no longer applicable. Instead, the process of a receptor accommodating a small molecule has been shown to be highly dynamic and time independent. As you can see in the left figure, the lock and key theory assumes that the protein and the ligand does not change during the binding process. However, this is not true. Both the ligand and the protein undergo some conformational change during the binding procedure. However, prior deep learning studies merely focus on a single stable and static complexes structures. They do not consider the time-dependent mobility. So how to capture the time-dependent flexibility? The molecular dynamic simulations is a very good option. And as we can see that watching the motions of individual atoms and perceiving them in a desired efficient fashion is experimentally difficult. You must pay lots of labors or monies to experimentally determine the binding process, right? An attractive alternative is to work with the computer simulations of the relevant biomolecules. And MD simulations seek to approximate atomic motions by Newtonian physics to reduce needed human labors. They predict how every atom in a molecule system moves over time based on a general model of the physics governing interatomic interactions. They can also be used to incorporate flexibility into docking calculations. So what's the aim of MD simulations? There are three aspects majorly. First is to study conformation flexibility and stability. That is what we use in this work. But apart from that, you can also observe response following controlled change to system, right? And you can also observe a dynamic process over time. That is called the ab initio MD, molecular dynamics. Apparently, ab initio MD takes much longer time than the first two ones, than just study conformational flexibility, because you need to start from the very beginning and run the whole process, right? So however, no existing work have proposed to equip deep learning models with MD simulations for more powerful capability in drug binding problems, and that is our contributions. So if we have the MD data, how to use it? The naive way is to use the self-supervised learning. But if you think about that, the cost of MD simulations is prohibitively high with the growing size. And as a consequence, a completely supervised paradigm of training and inference on MD's trajectories is invisible. In other words, that you can train your model on the MD simulation trajectories in MD data, but when a new sample comes, how can you deal with this new sample? You have to, if you use the self-supervised learning mechanisms, you have to run the MD simulations of the new sample, right? So this is invisible. You cannot, when a new sample come, you should always run this, and it is costly. So as a remedy, we use the self-supervised learning to endow the model with the capability to capture the time-dependent flexibility. And how to decide these pretraining tasks? We have three standard goals. First, the prediction task is reliable and easy to get. That is intuitive. And the second is that the predict target should reflect the temporal information within MD trajectories and is relevant to the drug binding. And last, learn the representations by through these pretraining tasks should be diverse and distinguishable. So let's review some protein self-supervised learning methods. And here like before, I classify them into sequence-based structures and some other based pretraining. The sequence-based researchers can very easily borrow the idea from natural language processing, like the mask language modeling. You mask one verse, you mask one residue, and you ask the model to predict the masked one, right? And there are very famous models like TAPE, the evolutionary scale modeling, ESM, ProtoChess, and etc. And for the structure-based pre-training, the contrastive learning proposed by Kermosler, Ropitsky. The idea is very simple. You just pick the substructures from the same, you regard the substructures from the same protein as the positive pair, and substructures from other protein is treated as negative pair. So you do the contrastive learning. And the self-prediction, oh, sorry, this is incorrect. This is paper from John and will be published at ICLR 2023. And this problem, this training mechanism is that you ask the model to predict some residual type, the edges, the distance, the angles, the dihedral angles. If you did not give this information to the model, so it's called the self-prediction. And some score-based pre-training, the idea is borrowed from the denoising diffusion probabilistic modeling that is very hot in computer vision, the generation of some images, the generation of giving a caption and your generation images, right? And just the target network is serves as the score network, and you do the pre-training. So very in contrast to all above mentioned mechanisms, our pre-training is a spatial-temporal pre-training. Okay, so let me give you an overview of our model, and left is the overview figure, and just to give you some notation and symbols. First, we do the MD trajectories using some software, and we get the trajectories, which consist of ligand graph and the receptor graph from t equals to 1 to t of 2 equals to t uppercase. And at each time step, you have the atom level graph of the ligand graph and the receptor graph. Each graph have nodes and edges. Besides that, you also have the edges between the ligand and the receptor. And each node has the coordinates, 3D coordinates, and the rotate translational invariant features, right? That is the basics of graph neural networks. And then we decide the first task is the future conformation prediction. The core idea is that we use the conformation of the next time frame as the target, and the models are required to forecast this prospective position. The idea is simple, but we make some key innovations to make these innovations on this task. The first is that we assume the Markov property. The Markov property on biomolecule conformation dynamics is assumed for ease of representation. We hypothesize that conformation at the next time step only depends on its last time step. So the loss is represented here. The condition is changed from the all previously conformation to only the conformation at the last time step. Besides that, we proposed prompt guidance. As you can imagine, the conformation change between adjacent time steps is relatively small, and long-term trajectories contain more dramatic information of complex flexibility. To this end, we design a prompt-based technique to consider both short-term and long-term temporal dependencies. That is, we add another feature named written as the H prompt, and this prompt is concatenated to the node feature, and this prompt guides the model to predict the conformation at t plus delta ti. So delta ti can be any integral numbers larger than 0 and smaller or equal than t minus 1. So you can use this prompt to indicate that the model can predict, instead of rather the next time frame time step, you can predict 10 time steps after or 50 time steps after. At last, we also perturb the input conformation with a little noise at each time step. That is, we add random Gaussian noise to both the ligand and the receptors coordinates. This noise perturbation has some theoretical and empirical spots. First, from the theoretical side, the denoising diffusion framework is strongly connected with the enhanced sampling method in molecular dynamics. In the enhanced sampling method, the energy is injected into microscopic system to smooth biomolecule potential energy surface and decrease the energy barriers. Secondly, from the empirical side, a simple noise regularization is proven to be an effective way to address oversmoothing of graph neural networks. This is proven in the noise node, proposed in the noise node, a conference paper introduced by Godwin. And last, from the biological side, the difference between neighboring snapshots is small, as I have already said before. So the perturbation plays a critical part in preventing overfitting and improving generalizations. That is, somebody.
Yeah, I have two small questions here. Like, first, I'd like to know, when you run the MD simulation, you take the MD simulation of the protein with the ligand. So why do you take the ligand there and not just do MD simulation for the protein itself? Since here you're trying to pre-train on protein trajectories, so why having a ligand there?
Oh, we run the MD simulations on the protein and protein ligand complex structures instead of only the protein.
Okay, so here the aim is to have something that is a model that is pre-trained to generate an embedding for the protein or for the protein ligand pair.
For the protein ligand pair.
Okay, that's something I did not understand. Okay, it's clear now. And for another question, like when you add the delta noise, because here you're looking at a trajectory, right? So if you add some noise, then you're at a different point in the trajectory. So I'd like to know, like, does is the noise that you add much smaller than the distance um, from the trajectory, like at a delta t time? What I mean is, like, if at the delta t, the protein moves by, let's say, in average 1 nanometer, and then do you add noise that is also at the scale of 1 nanometer, or do you go smaller or larger than that?
It's a good question. It's in fact the sigma, the hyperparameters, how to determine the magnitude of the noise is a hyperparameter. So you can tune it according to the model performance. But instead, when the target is a long-term trajectories, the sigma is relatively large. When the target is a short-term trajectory, the noise should be relatively small, right? Because short-term trajectory, the conformation change is very small, so you cannot add too large the noise.
Yeah, but at each time step you add a noise. So, oh yeah, well, I see what you mean. If delta t is bigger, then you add bigger noise. If the delta
Yes.
t is smaller, you add smaller noise. Okay, that makes a lot of sense. Thank you.
Okay. No problem. So this is the first task, and the second task is the protein level snapshot ordering. The core idea is that we ask models to find the correct order for a set of complex structures with which the whole sub trajectories had the greatest coherence probabilities. The task object is that we have a set of conformations. For example, we have conformations of five time steps, and we have some order t. And task goal is that we should find the optimal order t star, which has the highest probability than other orders. Here we use how to order this. We just follow ideas from the sentence ordering in natural language processing, named the topological sort ordering, a standard algorithm for linear ordering of the vertices of directed graphs. When the number of constraints becomes 2, it just become the task. The ordering method just becomes the next sentence ordering in BERT, right? In addition to these two Pretraining tasks, it is time to introduce our background model. Here we use the graph matching network. We just inspired by this. Our backbone is inspired by the independent equivariant EGMN, which is used in Equidoc. Here IEGMN extends both graph matching neural network and equivariant graph neural networks. It uses both inter and inter-node messages as well as equivariant coordinates updates. Here, I do not introduce the details of how this networks works, and I highly recommend you to read the original paper of Equidoc. But here we can just focus on the line in the yellow box. You can see that as Equidoc is used to dock two proteins, so the relative positions between these proteins are unknown. So the order only use attention-based coefficients to aggregate the messages between the protein and between the ligand and the receptors. However, in our case, we have the position relationship between ligand and receptors is is explicit, right? So we should design a new model that are able to fully explore information within cross-graph edges. In equidoc, it assumes that fully connected edges between the protein and the ligand. But in our case, the edges can be clearly defined by some distance threshold, distance cutoff, or by k nearest neighbors. So our modification is very small but intuitive. Is that we add a new term, also in the yellow box, the phi d, to integrate the distance information, namely the cross-graph edge into our graph neural networks. And then the model input and output is represented here. You feed the node features, the coordinates of both ligand and receptors. You can output some future conformation node features and the coordinates. So the above is the technical part, and let's go to the experimental part. First, let me introduce the pretraining dataset. Here we use the PDB for EMBO program to prepare the PDB files downloaded from the RCSB. And the 60 files are manually inspected by pharmaceutical experts at MindRank AI to determine whether they are suitable as protein ligand complex models. And as for the computational cost, it takes about an RTX 3080 GPU, roughly 20 hours to run 100 nanoseconds per complex with the periodic boundary condition in the NPT ensemble, and it will result in 10,000 steps per complexes. And here, notably, we only use the pocket part as the model input instead of the entire protein in ProtMD. There are two major reasons. First is that the pocket is the most crucial region where the protein interacts with the ligand, and it undergoes the most violent spatial change during the interaction process, and it can reveal enough information about drug binding. Another reason is that the pocket is much smaller, and it contains far fewer atoms than the integral protein. So the pre-training speed is significantly fast. Here we choose two downstream tasks. First is the binding affinity prediction, which is the mainstream task and is very well known. We just predict PK and well K is the binding affinity in molar units. And we use the same setting of the atom 3D with weighted protein ligand complexes such that no protein in the test has more than 30% sequence identity with any protein in the training data set, and resulting some in the speed of chain validation test to these numbers. And the second task is the ligand efficacy prediction, which is a binary classification task. And the models predict whether a molecule binding to the structure will be an activator of a protein's function or not. In other words, we just forecast whether the molecule bound to the structure can activate the protein or not. And we also used the same setting of atom 3D. We split the complex pairs by protein target. So the main result is posted here, and we report for the binding ligand affinity prediction. We just report the results of both linear probing and fine tuning, and it can be found that ProtMD achieves the lowest IMSE and highest Pearson's and Pearson's correlations in this talk. And also interestingly, that structure-based methods generally surpass the sequence-based and surface-based approaches. And for the ligand efficacy prediction, our model also attains the highest AU-ROC and AU-PRC. So apart from the main experimental results, a reviewer in our paper, when we submitted this paper to Advanced Science, asked that, how can our model work on predict structures? I believe this question is worth investigating because as you can see that all previous evaluation is acted on experimentally no complex structures. But when we deal with real-world applications in industry, and experimental structures are not always accessible. So some in silicon Glocky algorithms are adopted to predict binding poles. Here, we just use the equidoc, the best model at that time, to quickly locate the binding sign and the ligand points and orientation for all test samples in PDB. Know that we did not we use the experimental complex structures in the for training, but use the predict structures as the test. And we also delete 9 unsuccessful docking pairs because the distance between the ligand and receptor is too far. So there's no pocket exists. And the result shows that the generalization of our ability of our ProtMD is strong. Besides, we believe that the decrease in the performance majorly comes from the inaccuracy of the structure prediction methods. Namely, equidoc have the equidoc, the equibind. The equibind has a very high ligand RMC of 8.2 on average. So perhaps more accurate docking algorithm is preferred, but which is out of the scope, right? Of our scope. We just focus on pre-training. The second interesting point is that we want to quantify how our model learns the correlation between MD simulations and drug binding related properties, right? In other words, why our self-supervised learning mechanism is beneficial for downstream tasks. And it is, if you remember, our ProtMD performs transformers, our Bergman models perform transformations on both node features and the 3D coordinates. At the pre-training stage, 3D coordinates are used. And at the fine-tuning stage, the node features are used and participate in acquiring the properties of ligand receptor pair. So it is motivation for us to explore the relation between the outcome 3D coordinates and the properties like binding affinity for our ProtMD before fine-tuning. Here we compute the average predicted spatial shift between the input and output 3D coordinates. That is, we want to quantify how our model predicts the protein and the ligand will change, how magnified it will change. And the result shows that a negative correlation between the predicted spatial shift and experimental binding affinity. This aligns or in other words, accords with the biological and chemical findings terminologies. Because ligands with good initial binding modes are tend to stay stable during MD simulations. So this probe shows that our model, our ProtMD, correctly learns the correlations between MD simulation and drug binding related properties. We also investigate that how many trajectories does our ProtMD need. It is notable that we only use 60 protein-ligand pairs, but it shows the unexpected generalization to all 3K samples in PDB bind. So we investigate in influence of the number of pre-training samples on the performance in downstream tasks. And it can be found that for linear probing, trajectories of more complexes is of little benefit if the number exceeds 50. But for fine-tuning, more trajectories are promising to enhance our model. At last, I want to show the ablation study and visualization of our model, and it can be observed that both self-supervised learning tasks contribute to the efficacy of learned representations, and the noise check and the prompt check are very useful for linear probing than fine-tuning. In the two plots below, we envision the representations by mapping them to the 2D dimensional space by PCA and the Tisney algorithms. And even without any information, our learned representations follow some kind of patterns that is strongly related to the drug binding related properties. Finally, I want to introduce three potential research directions of our future work. Right. First is that from the data side, we can use ab initio molecular dynamic simulations for pre-training models, but it will take more computational resources, computational costs. And you can also devote more GPUs to generate trajectories of more complex structures. Because as we demonstrated before, that more complex can lead to better performance. And the second one is that from the architecture side, we can develop more advanced heterogeneous geometric graph neural networks. And the last is from the biological side, we can design more robust technique to those non-experimental conformations. Thank you. This is my representation, and this is my email for international friends and my WeChat for Chinese friends. If you have any issues want to communicate with me.
Yeah, thanks a lot for the presentation. I think it's very good. It's really nice to see some models that are like really based on the physics of the protein and not just pre-training on language model, for example, and tricks that were beneficial in computer vision or in language modeling. And I think like seeing this correlation between number of proteins and the performance shows us that like right now the only reason your method is not performing so much better than everyone and it's just like a bit better is because they have millions and millions of data points, and here you're focusing only on like 60 proteins. So I'm really eager to see like what would happen in the future if we can scale that up. If you go on the slide where you discuss the number of proteins in MD simulation, I would like to know how many protein ligand pair there was. Like for each protein, how many pairs did you use?
For each pair, how many how many time steps?
No, not how many time steps here. Basically, do you have only 3,000 samples? Like, so
yeah,
if you
the
have
downstream tasks for the downstream tasks, we only have three. We will only have 3,500 as the training, which is mined from the PDB bind.
Okay, and for how long were the simulation ran? And do you think that longer time simulations would be beneficial also, or this is the enough to get the model to be pre-trained?
Yeah. In fact, there I think as for our non-initial molecular dynamics MD simulations, I think maybe 100 nanoseconds is enough. But for the initial MD simulations, it must take longer, right? But I'm not an expert in these areas. All the MD simulations are run by the company MD MindRank AI. So I just proposed. I'm responsible for the deep learning side.
Okay, perfect. Thanks a lot for the answers. I have a few more questions, but I will first ask the audience if they have any question related to the work.
Okay, thank you for listening.
So if there's anything, please raise your hand or write in the chat. Okay, I guess I can ask my questions then. So if you go on the plot where you show the correlation between the distance, I think the previous slide. Yeah, this one. Predicted change in position and experimental binding affinities. So here it's how do you get the predicted change in position? Is this by running like the entire MD simulation with the ProtMD, or is it only for a few time steps? Like, how many time steps do you need to have this predicted change of position?
As for this one, we just predict you feed the complex into the model and predict how large the spatial shift is. So there's maybe no time step. Oh, okay. You mean the prompt, the prompt, which sort of prompt you given to the model? Does it predict?
Sorry, I was on mute. I'm asking when you do the predicted change in position,
Yeah.
how many, like, do you only look at one time step with ProtMD?
Yeah. Well, in this analysis, we just ask the model to predict the conformation in just one time step.
Okay, in just one time step. So it's very interesting because it shows like if in one time step only there's a lot of change in position, then it means it's not locked in place correctly and doesn't have a strong binding affinity. I would have expected to see more time steps as well. That would have been super interesting to look at, like whether one time step is enough to see the change, or whether more time step give you a stronger correlation.
Yeah, I understand that.
Yeah, no, but I think it's very
The
interesting to see.
the x-axis is magnified by some constants, so to make it larger instead of yeah.
Okay.
There's one question in the chat board is that the Dr. Ma asked, would this model be beneficial if trained on protein itself? I'm not sure, but some companies in China has reached out to me and they want to do this to transfer our ProtMD to protein molecular dynamic simulations. As you see that we only do pretraining on protein small molecule simulation, and then they want to do protein pretraining. And if we train only on the protein itself, I think the insight should be related to your downstream tasks. What information you want to capture? In our case, we want to capture the conformation change, the flexibility during the binding process. But if you only have one protein, you don't have the interactions with other molecules. So the goal of your task should be is definitely different from ours. So I cannot figure out currently, but I think you might take a try in your specific problem.
Yeah, maybe Shuhao would like to unmute himself and ask the question, or he says, I am thinking of how residues interact within molecules. Like, I guess,
So why?
Go ahead.
So if you want to understand how they interact with molecules, why not just follow our patterns instead of train only on the protein itself?
The question
okay,
was,
it's residual level, right? It's in the residual level, but you
I
just
think,
build.
sorry, I think the question is about the residues of the protein itself. Like, I'm not sure I understand exactly where this question is headed, but perhaps like one thing about the question could be like, can this be used on the protein itself just to do a protein model that competes with ESM, for example? Like instead just having a pre-training to generate an embedding of the protein. Yeah.
But ESM is a sequence-based model, and it explicitly encode the 3D geometry, right?
Yeah, it does not encode the 3D geometry. The question is whether this could be used to replace ESM, because ESM is used also to do binding predictions. So like, could you use this instead? Like, or can you use this molecular dynamics to learn things about the protein that are not captured by ESM?
I know. Perhaps my answer may not be correct, but from the deep learning side, you can just build the residual level graph and the atom level graph, residual level graph for the protein, and atom level graph for molecules. So for the residual level graph, the graph neural networks can be well trained if you maybe do I express my idea clearly? Just to separate these two. In our work, we just use the atom level graphs for both ligand and receptor. But if you only focus on the residual level, you just build the residual level graph for proteins.
All right, that makes sense for me. Is there any other question from the audience, or Shuhao, if you would like to give more details, feel free to unmute yourself.
Sorry, yeah, I was thinking like your model is also a residual level, right? I'm thinking like if this model can be applied to kind of generate a residual level like embeddings, so that we can kind of like the scenario I'm thinking about is like after the protein binds to like certain molecules, there are like interactions between residuals within the protein, which kind of like give rise to some changes in terms of conformation state. Do you think your model could do some like this kind of task where like for example allosteric effect, like when a protein binds to a molecule, it can undergo a certain conformational change, and then if is it possible that this pretraining network can be applied to that kind of scenario?
I believe so. I believe so. If the conformation change follow the physical rules, just like the Newtonian rules, I think the conformation flexibility information can be generalized to your task learned by in the pretraining stage, can be transferred to the downstream task you described.